And now we have Alesia Herasimenka that will talk us about the impact of the optical properties on the controllability of solar sails. And go ahead.
Thank you. So I work at University Côte in France, and we are working on controllability of solar sails. So first, let's define what is controllability and what are solar sails. Solar sails are satellites that use solar light in order to navigate in space. So we have a flux of photons which arrive on the surface of the sail, which is very big and the sail is very thin. And they are reflected or absorbed by the materials. And by this, they push the sail in the same direction that the incident light. So why solar sails are interesting? Because they don't need any propellant, and they can be used for a very long time missions. So now, what does controllability mean? Actually, it means that you can take your system from a given initial state x0 to a wanted, desirable final state xf. So imagine you have a car. You can go forward, backwards, turn on the left, turn on the right. So you can go everywhere you want. The same with the satellites. Saying that it's controllable, it means that for a given initial orbit x0, I can create a control that will bring me to the final orbit xf. Now, why this problem is complex? The thing is that our control set is delimited. Imagine you have a car that can only go forward. So you're not controllable, right? It's almost the same in our case, because we cannot create a force which go toward the sun. So we have the photons which push this satellite only in the opposite direction. And if we can control the sail by changing its orientation angle, and all possible forces we can create are represented in blue here. So it's delimited by a convex cone, which I put in red. So first I'm going to present briefly the dynamics of the system. Then I'm going to show you the condition for controllability that we formulated. And finally, the results that we came up with, which are actually the minimum requirement for the controllability. So first, what is the solar radiation pressure? As I said, you have the photons coming on the surface of the sail, and you have two main components of the sail, of the force. First, you have photons which are absorbed by the material and that push the sail in the same direction as the incident light. And then you have a part of photons which are reflected from the material and will push the satellite in the direction which is normal to the surface. And the final force is basically the sum of these two components. Now, let's rewrite our system as a classical control problem, control affine problem. So we have our state x dot, which is equal to f0, the vector field f0, which we call drift, because it doesn't independently control, plus the sum of vector fields fi multiplied by the controls ui. As I said, our control is the angle of orientation according to the sun. So we decided to modelize our control as a normal vector to the surface. So by changing the orientation angle, all possible forces we can create are represented in blue. So this is what we call the control set U. Now let's parameterize the control set. Its size actually and its shape depend on the reflectivity coefficient. The more reflective is our solar sail, the bigger is the control set. So this is almost a perfect sail, which we call a mirror model, for which the reflectivity coefficient is almost equal to 1. And then you have another extreme case, which is an absorptive sail, for the very small reflectivity coefficient. So now, let's parameterize the dynamics of the system. Actually, our state are orbital elements. So we have parameterization of the orbital plane. We have three polar angles and the shape of the orbit. And then we have also what we call a fast variable f, which is actually the position of the satellite on the orbit. So it varies from 0 to 2 pi. The equations are given by what we call Gauss variation equations. Those are actually equations that allows us to introduce perturbations in our Keplerian motion. So we made two assumptions in our model. First assumption is that we don't consider solar eclipses, which can seem as a very big assumption, but actually it's not, because we are interested in proving non-controllability of the system. So even if our system is not controllable without solar eclipses, it will surely be not controllable with them. So we kind of underestimate the results. And the second assumption is that we don't consider the motion of the sun over one orbital period, because it's very small, so we can neglect it. Finally, let's talk about the classical approach. First, some definitions. Lie brackets. If we have two smooth vectors, f0 and f1, Lie brackets, it's actually a permutation of two matrices. So you can see it have AB minus BA. The matrices are not commutative. And actually, it allows you to see where you can move the directions in which you can move your state. So if you do Lie brackets iteratively with all possible vector fields of the system, you will create a span of all possible directions, what we call Lie algebra. Finally, the second definition is controllability. So as I said, saying that the system is controllable means that I can bring my state from an initial position x0 to a desirable final position xf in a finite time t. So why can't we use a classical theorem of controllability? Classically, you say that the system is controllable if the three conditions are verified. The first one is that the drift of the system is periodical. It's our case because if we don't have any perturbation, after one orbital period, we will come back to the same position. The second condition is that the Lie algebra is of the full rank, so the system is what we call breaker generating, and it's also our case if our sail is not perfectly absorptive sail, but it's not a realistic case. But the third condition states that the convexified control set must be in the neighborhood of the origin. So our control set is in the blue, U, as I said. The convexified control set will be a cone with which we approximate our control set. But as we see, it is not defined in the neighborhood of 0. Again, we cannot create the force toward the sun. So that's actually the main reason why we can't use this classical approach. So our idea was to come up with another condition for controllability. And to do so, the first thing we did is to say that we're going to approximate the control set by a cone, as I showed before. So for given optical properties of the sail, we can define a convex cone, represented in red here and here, which is parameterized by an opening angle alpha. So finally, the proposition we formulated is that if the three conditions are verified, the system is controllable. First, the system must be breaker generating. Secondly, the control set should contain the origin. And the third condition basically says that you can bring your system with the convexified control in all desirable directions. I will not go into details the proof of this proposition, but we wrote a preprint on it, and it basically uses theorems of the geometric control and the closure of the Richman sets. So, to recall, we can't use the classical approach, so we proposed another condition. The first is verified, the second is verified. By definition, we need to verify this condition. How can we do this? To do so, we decided to formulate an optimization problem. So actually, if there exists a one-form PI, which scalar product with the derivative of the system is strictly positive, then the system is not controllable. It means that there is a direction in which you actually can't go. So you have your state, and there is directions where you cannot move your state. So to do so, we formulated an optimization problem. We want to find out some coefficient g, we want to maximize it in order to make this product bigger than g. So for all positions over one orbital period and for all controls on the convex cone. If the solution is strictly positive, then the system is not controllable. How can you see it geometrically? If you take a very poorly reflectable sail, then the cone will be very small, the opening angle is very small. And then by increasing reflectivity of the sail, you will open your cone more and more. And finally, at some point, your coefficient g will become equal to 0, and it means that the system will be controllable at that point. So for the given initial conditions, this example says that if the cone angle is more than 45 degrees, our system is controllable. We can easily come forward and back from the cone angle till the optical properties. So again, we have this optimization problem, but we have two main difficulties. First one is the semi-infinite convex problem. So we have two infinite variables, which are position on the orbit and the controls, because you have an infinite number of controls on the cone. And the second problem is how to ensure the positivity constraint. So the first thing to do is that we basically discretized the control set. So we discretized the cone, and our controls are conical combinations. Second, we can transform our dynamics to make it exact trigonometric polynomials in F. So we don't need to discretize this, we can just use Fourier transform. And how to ensure the positivity constraint, we leverage on formulas of such called squared functional systems derived by Nesterov. So it helps us actually to transform this problem into a finite number of LMIs, linear matrix inequalities, what we know how to solve. So let me present the results we got. Just to briefly, how can we parameterize the model, the orbit? We have three Euler angles that orient the orbit according to the sun. Then you have a semi-major axis, which is the scale of it, and eccentricity, which shows how circular or elliptic is the orbit. So the results we've got are represented here. First of all, they don't depend on the first Euler angle, so it's independent from it, and as well as from the semi-major axis. So we have only three state variables which influence the results. And what is the most important thing to understand here is that the final maximum minimum angle, as you can say, is less than 90 degrees. What does it mean? It means actually that you don't have to make it perfectly reflective sail to make it controllable. Because a perfectly reflective sail is not a realistic case, but we don't need it. So with the models we can produce, we can make it controllable. And to give an example, there is a model proposed by NASA, and we took the optical properties, we transformed it, and we got up the result with 58 degrees. So it satisfies almost our condition for a lot of different orbits, but not for all of them. So to conclude, what we did is that we proposed a new way of verifying controllability of control set of the solar sails. And the result is that the sail doesn't have to be perfect. Our results are also planet independent because they don't depend on the gravitational parameters. So it means that whether your sail is around the Earth or around the asteroid, it works. And we propose the minimum angle alpha, which can be transformed into optical properties of the satellite. So here are some references I used, and thank you, and I hope you enjoyed.
Thank you, Alesia, for the wonderful speech. As always, is there anyone with any doubt about the talk we just did? Any question? No one? I was finishing this presentation. So, yeah, we are.
Because no one understood nothing? Or
yeah. No, in my opinion, we are just all very, very tired. It's been a long, long week. So now, okay, we can thank you.